All right, so this is a problem where it does involve the apparent weight. We've got an astronaut standing on a scale in a spaceship, and the spaceship is accelerating upwards. So it's like being in an elevator, just a real powerful elevator that's going to be accelerating very quickly. But we've already done a problem like this before, where we actually had to do a bunch of work just to calculate the acceleration so that we could then figure out what the apparent weight of the person was in the elevator. In this one, they're just giving you the acceleration, so I don't have to do all of that work. All I have to do in solving this problem is I'm just going to make this, pretend this is part of the rocket. And so we're going to have a person, the astronaut, is going to be in the rocket and standing on a scale. Now the scale is going to be the apparent weight. The normal force on the person is what the scale is going to read. So the two forces that are going to be acting on the astronaut, it's going to be his weight, it's going to be down, and the normal force is going to be up. And so this is the weight, which is not given in the problem. The acceleration is given. So the acceleration is given as 30 meters per second squared. And the mass of the astronaut is given. So that's 70 kilograms. If I know the mass, I can get the weight. And we're looking for what does the scale read upon takeoff. The scale is going to read the normal force. Okay, that's what the normal force is, the apparent weight. It's what you appear to weigh because you're standing on a scale and the scale is reading something other than your true weight. It could read your true weight. I mean, once this rocket starts moving at a constant speed, it's going to read your true weight because the forces would be balanced. It's only going to be different. This number here is only going to be different than that when the rocket is accelerating. And at this point, it's accelerating at 30 meters per second squared. So if I write my descriptive equation here, it's going to be what? What's my descriptive equation? Right, Fn minus W equals Mn. And Fn's the unknown. That's what the scale is going to read. Or if I said, what's the apparent weight of the astronaut, that would be the same question. I know the M, I know the A, I don't have W. So rather than even solve for W, I'm just going to write W as mg so I can just plug it in. So, I mean, the W is not needed. If I want to solve for the normal force, then what I'm going to do is I'm just going to move the W to the other side. So the MA is already over there. And when I move W to the other side, so when I move this to the other side, I'm not going to write plus W. I'm not going to write plus W here. I'm going to write plus mg, which is the same thing as W, but now I don't have to solve for W separately. And then I can just plug in the numbers, and those are going to be the answer. That's going to be the answer. So Fn is going to be Ma plus mg. So the M is 70 kilograms. Which will go there and there. The A is 30 meters per second squared. And the G is 9.8 meters per second squared. So if I look at this, this would just be enough force to support the astronaut if when the rocket's on the launch pad, the normal force would equal 70 times 9.8. When the rocket's moving at a constant speed, the normal force would be equal to 70 times 9.8. This amount right here is the additional amount that we need in order to accelerate the rocket. So if you plug in your numbers here, you're going to get 2100 plus whatever that other one is. Looks like 686, so 2786 newtons. That's your normal force, which means that's the apparent weight, which means that's what the scale is going to read. Any questions? Yes.
So if you factor